Hello, in this video, we will talk more in detail about Poisson random variable. So we know a random variable, if taking on one of the values, these are integer values, 0, 1, 2, 3, and so on, have the probability mass function given in this expression. So P, the probability of random variable equals a particular value, and this value I can be 0, 1, 2, 3, 4 integer values, equals E minus lambda in power and I factorial in denominator and lambda I in power. If has this expression for the probability with particular integer variable values, then this random variable can be said to be a Poisson random variable. So here the E is a factor, the Euler factor 2.718, and the lambda is a constant, and I means factorial. And here this I, so this exclamation is a factorial, and this I is for different values for the random variable. So it's quite clear. E minus lambda I divided by I factorial. I can be 0, 1, 2, 3, and so on. And if we make a summation of all these probabilities given as the Poisson random variable, then we can say I equals 0 to positive infinite, then Pi summation equals E minus lambda and summation with this expression, because this is the expansion of x with respect to I, then we can get this expression is E lambda. So E lambda times E minus lambda equals 1. This also verifies that in the preceding Poisson random variables, probability mass function is correct. And the mean and the variance of a Poisson random variable. To determine this, we have to use moment generating function. So moment generating function's expression is the expectation. Means expectation of E tx. So here t is a constant factor and x is a random variable. So if you want to know the mean and variance of a random variable x, we can calculate E tx first. And for the Poisson random variable, so we just make some transformation, and we can get this equals exp, here also E, then inside E, this brace is lambda times Et minus 1. Because we want to get expectation, so we will use the probability of Poisson random variable. Then finally, we can get the moment generating function for the Poisson random variables equals this one. Then, according to moment generating functions to mean and variance, we can use differentiation for the first order differentiation and second order differentiation. Though we can get both a little complicated, especially for the second. But next we will evaluate these expressions at 0. So Ex equals first order differentiation at t equals 0. So the expectation of Poisson random variable is lambda. And the variance of Poisson random variables equals the second order differentiation of the moment generating function. Evaluate the t at 0, then minus the first order's square. So first order is expectation of a Poisson random variable. So finally, we can get the variance of a Poisson random variable is also equals to lambda. So Poisson random variable is very interesting. Both mean and variance have the same parameter. So there are only one parameter in this distribution. And the Poisson random has a wide range of applications. And one application is we can use Poisson random variable to approximate a binomial random variable with n and p. So we know binomial random variable is n numbers Bernoulli trial, and with each trial has a success rate p. So the binomial random variable is the number of how many times occurred for the true case in the n trials, right? And each trial has a probability p for the success rate. So when n is very large and p is small, so it's very unlikely to happen, the case. So we can use a Poisson random variable to approximate a binomial. Here is the inference of this application. So first, this is the binomial random variables, px equals I. So we just use the definition of the binomial random variable, then make expansion of this expression. So next, if n large and p is small, so this expression equals 1, approximately equals 1. And we can get finally the probability of a binomial equals the expression of a Poisson random variable. So here lambda equals np we can use. So lambda in a Poisson random variable means in a predefined time of, for example, any volume, in a predefined, for example, 1 hour, and average occurring times. For example, in 1 hour, there are almost approximately average one telephone coming in the call center. So this lambda is np. And p is a very small constant rate. But in a predefined time interval, so np is the lambda. So for example, 10 hours, there are 2 telephones coming in. So if we define 10 hours, this time interval, so this lambda is 2. So there are many types of application for the Poisson random variable. Practical examples, for example, long telephone numbers are dialed in a day, and people in a community living to 100 years of age. If this community has a predefined how many population, right? And the number of customers entering a post office on a given day. So this given day is a predetermined time interval. So all these are random variables, and all these fulfill the presumption that we have a constant rate on the predetermined time interval. So next we will take a look at one example. Suppose that the average number of accidents occurring weekly on a particular stretch of a highway equals 3. So calculate the probability that this is at least 1 accident this week. So this is a predetermined time interval is 1 week. And we know the average is 3. So here 3 is lambda and equals np. Is lambda. And the solution is we can use Poisson random variables to model these occurring times, this random variable, how many accidents occurring on this highway during a 1 week. This can be 0, can be 1, can be 2, can be 3, and so on. So if we want to know at least 1 accident this week, we can just use the probability of 1 minus there is no accidents in this week. So probability of x0 is this expression. So we just use 1 minus this expression is about 0.95. So we say if the average number is 3 in a given week, so there is almost 95% of the probability occurring at one time in this week. So very low, almost 0.05, about 5% of the case that there is no accidents in this week, right? Thanks for watching.